Okay, so we are all set. So I again welcome you to this webinar. The topic of this webinar is the release of the new features of ATENA version 5.7, which we have released this fall, and it can be downloaded from our website. So I will cover the topics as they are listed, shown on this slide. So first I will say a few words about our company, because there might be some participants which are new to ATENA, about what we are doing. And then I will give a short overview of ATENA products, mainly for the new guys in our webinar today. And then I will cover some of the new features. The main new feature in the new ATENA are the durability models, new models for the fibre-reinforced concrete modeling. We have a new small program which can be used for testing materials and investigating their behavior. I will mention also the possibility to use ATENA on the cloud. And the last topic will be some new development and summarizing the features of beam and shell elements and how they can be connected to solid elements. So for those of you who are new to Cervenka Consulting and ATENA, so let me first say a few words of what we are doing. So we are developing technologies and software for the modeling of reinforced concrete structures, starting from small samples or laboratory experiments up to large-scale analysis, as are shown on this slide. So bridges, nuclear containments. Recently, we are also involved in projects dealing with offshore wind power plants, where, of course, they are usually from steel, but there is grouting connecting the top part with the bottom part. And this can be nicely analyzed also with ATENA. And also our fatigue model can be used there. Well, there is a picture from Prague in autumn. So we have autumn now in Prague, so that's how the trees are nicely colored here. Yeah, by the way, this is not our office, what you see on the picture. This is the Prague Castle. This is the office of our president. So we are a small company, about 20 engineers, most of them with a PhD degree. But we are small, but we have many international activities covering almost the whole globe. Here you can see where ATENA is being used and where we have our distributors. Short summary about main features of our material model. So as we know, we are covering concrete, so we need to have a good model for concrete. So on the left, you see the failure criterion for concrete in 3D space of principal stresses. So there it is a kind of a cone with a triangular shape, but with rounded corners. And then for cracking, to model the crack opening and development, we are using approach based on fracture mechanics. That means during the crack opening process or the crack development process, energy is dissipated, and this energy is called fracture energy. And to use this within the framework of the finite element method, we are using the so-called crack bend model. This is again the summary. So we have one model for tensile behavior based on the Rankine criterion. And the energy dissipation when the crack opens is controlled by this crack opening law with the fracture energy, GF. And in compression, we are using plasticity-based model with this William-Menetre 3-parametric surface. And this surface first expands, modeling the hardening phase of the concrete behavior in compression, and then there is softening. The softening in compression is also based on this crack bend approach. That means energy is related to the zone that is being crashed. So in this case, it is typically the finite element size. We validate this model mainly using the blind blind predictions. This is the best way. And here is a summary of our recent achievements in some competitions. So this was kind of an introduction, which maybe many of you have already seen. So I will briefly go to the most important part, which is, let's talk about the software ATENA, which has been now released in a new version. So what kind of products we have, because this may be sometimes confusing for first-time users. So if we look at it, let me maybe go first to the second slide, and then I will come back to the first one. So we have several products. One, let's say, historically older product is ATENA Engineering, which has two versions, 2D and 3D. And this program is, let's say, good for beginners. It's a good introduction to nonlinear analysis because there is a easy to use framework around it, user interface. So it is rather easy to develop a model for nonlinear analysis and obtain some results. But this, let's say, is our older product, which we still are distributing, but now we are more concentrating on developing this more advanced version, ATENA Science. So this ATENA Engineering supports only static analysis, 2D and 3D. And it is, let's say, suitable only for simple problems. If you try to analyze some very large structure or a structure with very complex geometry, you may have some problems. So for that, we recommend ATENA Science. This, in addition to statics, supports also dynamics, creep, and transport problems. By transport, we mean moisture and heat analysis. And this program is using a GID program for preprocessing. And then there are two programs, ATENA Studio, ATENA Console, which comes from our company. This GID preprocessing comes from the University of Barcelona. And this ATENA Studio and ATENA Console can be used as a runtime module and then also for post-processing. Actually, for post-processing, you have to use ATENA Studio. ATENA Console is basically a runtime program only for running the program in a console, as a console application. If you want to see graphics during the analysis, then you have to use ATENA Studio. Then we have other products. A very interesting product is SARA program, which can be used. Basically, this extends the nonlinear analysis of ATENA to allow to take into account the randomness of the input parameters. So it combines ATENA with program FREET, and this whole package is called SARA, and it allows you to make probabilistic simulation. We also have another new product called Material Driver, which can be used to investigate. I will talk about that more later, which can be used to investigate various ATENA materials. And namely, it can be used to test the user material. If you are developing a user subroutine, you can use this material driver to test it. So if I go back, this we can look a little bit at the technology. So if we divide those three phases of analysis, pre-processing, runtime graphics, post-processing. So if we are on the level of ATENA Engineering, for instance, using the ATENA 3D, everything is covered into a single environment where you make pre-processing, prepare the models, you run the analysis, and then you perform also the post-processing. Well, if behind the door, what happens is that if ATENA 3D preprocessor prepares the model, it creates a so-called command file with all the commands for ATENA. This command file has a typically extension INP. And then with this command file, you can run in ATENA, normally in ATENA Engineering, you don't see this file, but you can also export it. And then you go to the next step, which is running the analysis. As you know, in ATENA, the unique feature is that during the analysis, you can see what is going on. Those of you who are new, I will just show a typical screen that you see when the analysis, ATENA analysis is running. So this is what you typically see. You see how the cracks are developing, how maybe the reinforcement strains are developing, and how the load displacement diagram of the structure is developing. So this is runtime analysis in ATENA, as you see here. And as the program is calculating, it is basically creating binary files with results. If you are in ATENA Engineering, you don't see these files. They are all packed inside a single big file. But if you are using ATENA Science, you have an access to all these individual files. Once the analysis is computed, then you go to post-processing. So the difference is that in ATENA Engineering, you don't see all these things. You have only one file, one program. But if you go to ATENA Science, the situation is a little bit different. We are using program Git for preprocessing. This develops the command file. Then we use ATENA Studio to running the analysis. We have all these results from each step. And then we can do the post-processing in ATENA Studio typically, but it is also possible to run or to import the results into ATENA Engineering, or for instance, also into GID. So now let me cover some of the new development, the new features. So one of the major, let's say, improvement is that we really completed the development of these corrosion models, which have been there also in previous versions, but they have been further improved and say made more user-friendly in the new version. So if we think about durability, in reinforced concrete structures, it is typically corrosion. So this corrosion has several phases. First phase is called initiation phase. That is the time which takes, for instance, for the chlorides to propagate to the concrete, and it is the time before these chlorides reach the reinforcement. At that point, the corrosion starts. And the corrosion, this corrosive process, again, here we can identify again several phases. One important phase is the cracking of concrete cover. That means due to the development cracking of the cover, crack appears. Now the chlorides can propagate faster, which again speeds up the corrosion process. And then again, the next phase is the spalling. That means the concrete cover totally separates from the rest of the structure. And again, we have an increase in corrosion rate. So now how we model that in ATENA? Well, you know, or those of you who have used ATENA before, you know that we have for each reinforcement, we can have a discrete model. That means we can have a model, can model each reinforcing bar. That means at any point or at any location of this reinforcement bar, we know the distance of the bar from the concrete surface. And then, therefore, we can use relatively simple one-dimensional diffusion models to simulate the propagation of chlorides, or another possibility is the carbonation of concrete. And so that means we can simulate the diffusion of chlorides once they reach the reinforcement, as you see here on the right. This diffusion process also can depend on the existing cracks. So because we know the location of the cracks in our ATENA software, which may come from external loads, from bending. And due to the presence of these cracks, we have an increase of the diffusion. It's higher speed of the diffusion of chlorides. So that means at this location, the corrosion started earlier and much more corrosion has occurred, which is indicated by these red marks. So as you can see and maybe understand, if I go back to these phases of the corrosion process we talked about, that means that means the cracking of concrete cover and spalling of. So with this, let's say, quite macroscopic model, we cannot model these individual, let's say, very local effects. Of course, we could create a very detailed model to simulate for large-scale analysis. This is quite impractical. So what we have a little bit different philosophy. We say what is important for our structure. For our structure, it is typically not so important that a small 2 centimeter piece of concrete separated and is missing. What is more important is that now the corrosion rate increases. So we consider in our model the fact that at some point the spalling must have occurred because we know the cover depth and we know the time of the corrosion process. So we can use existing models to determine that now the spalling must have occurred. So the spalling actually is not modeled in ATENA, but we know that there is a high probability that spalling occurred. So we can increase at that point the speed of corrosion, rate of corrosion. So this is just, I want to emphasize this, that we are modeling the result of this corrosion process, but currently the ATENA model doesn't model spalling itself. So, but okay, so this, and then of course, what is the result of corrosion? It is the reduction of the cross-sectional area of reinforcement, which of course has is considered in the analysis and has an effect on the load carrying capacity. I will demonstrate that later on how this is done on some practical. Okay, so this is actually the example I was talking about. So it will be application to structural health monitoring. And for that, we'll use one bridge in Germany and another bridge also in Czech Republic. This is this one. So what happens is that we combine now this durability model with monitoring, yes, because it is always very important to relate our numerical model somehow to reality. So what happened is that some monitoring system was installed on these bridges. Here you see the view of this monitoring system. And this monitoring system allowed to not only measure the deflections of the bridge, in this case strains, as you can see, there are some strain gauges, but the system was calibrated by using some predetermined vehicles. And this allowed them to monitor long-term load on the bridge also. So here you, for instance, see a statistical distribution of the vehicle weight over the monitored period. This shows some pictures from this calibration process. So here you see the trucks with the predefined weight passing the bridge. This picture, you cannot see it very well, but this shows this monitoring system. And part of the monitoring system was also a laser scanner. So this laser scanner determined that the vehicle is passing, and it also determined how many axles the vehicle has. And from that, it was also possible to determine the type of the vehicle and make some classifications. So with this, we could use this information not only to determine the traffic or the load on the bridge, but we used it in these particular cases also to determine or to calibrate our model. So this is a situation of one vehicle with the detected weight passing the bridge. but we could, of course, we selected certain vehicles from certain weight ranges to calibrate the model using them. So here you see one particular path of the bridge. You see the crack development, crack opening and closing as the bridge is, as the track is passing. So this was used to calibrate our model. And then with this calibrated model, we use the previously mentioned durability model. This shows the model of the bridge with some chloride concentration conditions. You can see the chloride concentration from the bottom was different than from the top of the bridge, because we assume that there may be some de-icing activities in winter and so on. So the chloride concentration on the top surface is higher. Then we run this chloride effect on the bridge for various years. So here we see the collapse of the structure after 100 years of corrosion. This also shows the results you obtain from the program. So this shows the model of the reinforcement. This is one of the interesting capabilities of ATENA, that we can model each reinforcement. And with this durability model, we can now calculate what is the corrosion of each reinforcing bar after, let's say, 100 years. So number one means full corrosion. That means almost all the reinforcement cross-section area is gone. The blue color indicates reinforcement without any corrosion. As you can see, the blue color are usually the stirrups, which are in the middle. They are, of course, not affected by corrosion. So how do we determine then the effect of this corrosion on the structure? Well, we basically perform kind of load tests. So after always certain period of time where the corrosion is acting, we always perform a load test, considering the typical design load combination on the bridge. So if we do that at the beginning, we obtain of the structural life, we obtain this blue line, which indicates, let's say, the strength of the undamaged structure. And then if we go in time, after 50 years, we see there is certain effect on the strength due to the corrosion of reinforcement. As we go farther on in time, we see that in the end, there is not enough strength to carry the design load combination, which is indicated by this ULS line. So we can plot it also in a different way, when on the horizontal axis we have time, and on the vertical axis we have the strength or the capacity, load carrying capacity of the bridge. And there you can, then we can plot the strength of the structure at various times. In this case, we are using the safety formats for nonlinear analysis from the FIB model code 2010. With this approach, or one of the approaches proposed in this model code, is to make one analysis with mean parameters, another with characteristic parameters, and out of that we can calculate what should be the design strength of the structure, considering the reliabilities as they are defined, in this case in Eurocode. So with this approach, you can see that at about 100 years, we will have can expect that there is not sufficient reliability of our structure. And we, of course, have to consider that currently the bridge age was about 50 years. So it still had about, let's say, 50 years of service life. So this is the summary of these results from this application to some practical, this durability model to some practical problem. Okay, there are no questions so far. Good. So I hope so it looks like my explanation is very clear. or everybody's sleeping. Anyway, let's continue to the next topic. The next topic would be the fiber-reinforced concrete modeling. We had models for fiber-reinforced concrete in ATENA already previously. Usually we use the so-called user material for that. And I will show later on how such user material, I will just give you some hints how this can be used. But with this user material, it is sometimes difficult because you have to calibrate the whole low displacement curve. Sorry, the whole softening curve. This is what you see. In fiber-reinforced concrete, the main trick or main problem is to find out what should be the right softening law that I was mentioning before, that our concrete material in tension, the main tensile behavior is controlled by the softening law, which shows what is the stress transfer across the crack as the crack opens. W indicates the crack opening. So in case of normal concrete, we have this kind of softening law indicated by this exponential curve. But if we once we put fibers into concrete, we typically obtain this kind of behavior with a much longer tail. And with our user material, we can basically determine what should be the suitable shape of this softening curve, which is, let's say, can be done, but maybe sometimes too difficult. And realizing that the softening law is typically this shape, we may simplify it by such a rectangle. We are adding such a rectangle as additional fracture energy to our model. So this is, let's say, simplification, but it may work well in many cases. So a new model has been introduced in ATENA now, which contains this simplified model, which makes it a little bit easier to use it in practical analysis. So again, let me summarize it. When modeling fiber-reinforced concrete in ATENA, there are basically two possibilities, either using so-called user material model, where the softening curve can be defined as a bilinear relationship. So almost anything can be defined here. But for many typical fiber-reinforced concrete, either with steel fibers or with plastic fibers, it is quite advantageous to use this simplified approach, where we just model effect of fracture energy as this additional effect of fiber reinforcement as this additional fracture. So how this is done? So we have for that a new model in ATENA, which has these two additional parameters, this additional fracture energy and this limiting crack opening. So that means this limiting value of the crack opening. So if we know the fracture energy, which is the area, we know this limiting crack opening, which can be nicely related to the fiber length. We can determine what should be this residual tensile. So this is the new material. Here I'm showing one example how it relates to some experiments. So if we typically in fiber-reinforced concrete, such 4-point bending experiments are used to characterize the material, and we are, in order to make the analysis, first we typically have to make an inverse analysis to fix or to find our softening law such that we can fit this 4-point bending test. So here you can see the fitting. In the case we are using this added fracture energy approach. So I think you can see it can nicely fit. Of course, there are some differences, but we have to understand that there is typically a quite large scatter in the experimental results. Anyway, for comparison, you can see here this dotted or not dotted, but dashed blue line, which indicates the response if there will be no fibers. Of course, we nicely see here the effect of fibers and how they improve the ductility of the material. Yeah, so this is, let's say, the different approach from the traditional approach, where we have to calibrate our softening curve based on these 4-point bending tests using the user material. And for that, some of you may have used before this fibre-reinforced tutorial, which gives you an idea how to do that for this user material. But nowadays, we are also working on a new software, which is, let's say, available for beta testing. If somebody is interested, we can provide this software to you, which basically allows you to make this fitting automatic for this more advanced user material. This program is called APIS FRC, and this will be available in the future versions we expect at the beginning of next year. So here you see the result of such a fitting, where you first start with this initial fit, which is the blue one. The yellow curve is the measured one. And let's say in 3 iterations, quite quickly, the program can obtain quite nicely very good. And here, this shows some application of this fibre-reinforced model to some practical cases of tubing tunnel construction in Czech Republic. There is some question by Asdam Tambuse, so let me answer that. Is there any new practical input parameters for strain hardening cementitious material like FRC? Well, I'm not sure I understand the question, but I think this is exactly what this new material is about. This new material makes it more simple, because before you had to use the user material and make this kind of inverse analysis. So of course, you can still do that. We also have this new tool which can help you with that. But there is also this another more simpler material model, which allows you just to define this FRC effect by these additional parameters, which is the fracture energy and this residual crack opening. And if I show you how this looks like in ATENA, if I switch to preprocessor and you go to the material definition, and we define our concrete material. So now there is a new type when you select FRC. And if you do that, there is a new dialog for tensile FRC, which contains this new material. And there are some predefined generation tools. So for several selected fiber types, for instance, if you select the Dramix, you define your concrete strength and the amount of fibers in kilo per cubic meter. It will generate you these parameters. So this is, I hope, the answer to your question, that we have introduced some simplification. Either there is this new material based on this added fracture energy approach, and we are also working on this tool, which can also help you to fit or to find out what should be the suitable softening law for the given fiber reinforcement, because there are many fiber reinforcement types available. I mean, many fibers available on the market, a lot of concrete types available on the market. So the best way is always to make such an inverse analysis, to make fitting to the 4-point bending test, which is a standard test which the material producer usually provides. All right, so now let me go, if there are no questions, let me go to the next step, which is this material driver. So it is a new program which you can start when once ATENA is installed. And with this program, you can basically, as you can see here, define a definition, write a small input file containing only the material definition, and then you can test it. Select some ATENA material type, either from the existing materials, or you can, this is especially useful when you are developing your own materials using the user materials subroutine. And then you can here define the loading. You can, it is like testing one material point. So that means like testing a cube of concrete, let's say, or cylinder of concrete, and defining a stress. You can define strains or strains. This is very interesting that at each step, you can control what you define. Either you can define strains or stresses, and then you can define various loading paths and see how the material responds. And here on the right, you have a view of the material state variables. You can always check how they change, what is happening. So it is an interesting small tool, which especially those who are developing their own materials may find useful. The next topic I wanted to mention is this ATENA Cloud. So what is it? It is a possibility how to run ATENA remotely. Of course, it may not be so interesting for our current customers who already have ATENA on their computer, but it may be an interesting availability for those who want to try ATENA. So you can log into this website, atenacloud.cervenka.cz. There you can create an account. It takes some time because we are right now we are verifying the requests, let's say manually. But after, let's say, 1 day, typically you receive the verification and you can log in. And there is a possibility to create a virtual computer. You can select some predefined configurations with the amount of CPU, amount of available memory. Once it is created, so here you see there is a list of computers that you can create, typically maybe one, or you can create more. You can connect to it, and once you connect to it, basically it's like a computer, virtual computer on the network. And when you log into that computer using the same credentials as you have for ATENA Cloud, you basically have you can run ATENA. You have a full access to ATENA. There is even a sort of a small dialogue for quick orientation, where are various examples, tutorials, and manuals. And you can prepare your model with ATENA Engineering or with GID and run the analysis. So it is maybe an interesting option, especially for those who are new to ATENA and want to test it. It is not fully, to clarify things, once you log in, you receive some initial free credits. But of course, if you want to use it for a longer time, you have to purchase additional credits. Into the future, we maybe also an interesting option that we plan to put some powerful computers. So you can, for instance, have here a possibility to have a computer with 32 CPUs and 64 gigabytes of RAM. So it may be also an interesting option for existing ATENA customers if they want to run some really huge analysis. So this is, let's say, future development. It can be done, but so far there was not a big interest in that, so we have not activated this option. But if somebody is interested in that, it can be done. The last topic in my presentation today is about the beam and shell elements. So I want to summarize this a little bit in more detail. What does it mean? It means that in ATENA, typically we were using these solid models, like you see this top part. So this is a very simple example of a beam, which typically we model by solid elements, either 3D elements or 2D elements. In that case, of course, you need to have at least, let's say, 4 elements through the height. In 3D, also some elements through the thickness, so it may require quite significant analysis time. So when developing some large models, this may not be a feasible way if you want to model the whole building, for instance. So in ATENA now we have some other possibilities. Okay, so if I start moving down, of course, the first possibility, if you want to have less elements, is to use quadratic elements, either 3D or 2D. This is, of course, a feasible option, but still it may require a lot of elements, a lot of analysis time. But now in ATENA, we have a possibility, or it has been there also for some time, but we are continuously improving that, to use so-called 3D shell elements. And recently we have introduced also the standard 2D shell element. So this is like the same beam. Now you can model as a small plate. Of course, it makes no sense to model a beam as plate, so maybe better to use these beam elements. And again, this beam element we have again in 2 forms, as a 3D one or 1D one. Well, what is the difference between 3D beam and this 1D beam? From the formulation point of view, there is no big difference. Both elements have rotational displacement and rotational degrees of freedom. But these rotational degrees of freedom are kind of hidden in this 3D version. Rotational degrees of freedom are translated to only displacement degrees of freedom of this 3D element. So it is this 3D formulation both for the beams and for the shells. The main feature is that they, on the outside, have only displacement degrees of freedom, which makes them easy to connect them to other solid elements. But internally, these displacement degrees of freedom are translated into rotation. And why this is useful? Because then you can model these kind of combined models. You can create these kind of combined models. That means if you imagine this kind of part of a frame, we can use shell elements here in the middle of the plate to model the bending behavior. So there we expect mainly bending. For the columns, we can use beam elements. And then for these areas of the plate column connection, where maybe shear failure will be important to capture, there it is advantageous to use solid elements. And of course, nowadays it is even possible to model this plate part and this column part also by standard 2D shell elements or 1D beam elements. So quite complex models can be created, connected together. And now let's talk a little bit about the connection. So in order to facilitate the connection of these 1D or 1D beam elements or 2D shell elements with the solid elements, we have new connections in ATENA. Be able to create, for instance, this kind of hinge connection or this kind of moment connection, or create these kind of structures where we combine beam elements, maybe with some solid modeling of the critical corner. So we generally have a problem that our solid elements, they have only displacement degrees of freedom, but these beam or shell elements, they have displacement as well as rotational degrees of freedom. So these rotational degrees of freedom have to be connected properly. And we have two types of connection for that in ATENA. So one is so-called fixed contact. That means you say that this beam node is mastered, is a master node, and we are connecting these solid elements, which is, let's say, slave in this case. So what happens is that the program, if you use this connection, it kind of recognizes that this beam element is actually not a line, but it typically has some height and width. And then these nodes of these slave nodes are connected, or it is detected that they fit somewhere into this beam element, and this is then used to connect these rotational degrees of freedom. Of course, there are some equations, complicated equations, but the basic principle is like this. And then there is another option, which is typically used if we want to connect the beam to the solid. This top option is good if we are connecting the solid to the beam. That means the solid is the slave and the beam is the master. But sometimes it is better to do it the other way around. So that means the beam is the slave and we want to connect it to the master, which is the solid. And there are two new connections for that, called 1D beam or 2D shell to solid. And they again work in a similar way, that they always recognize that actually the shell element or beam element has a certain thickness, and it has these virtual points on this through this thickness, and it is searching how they match or how they fit into the master part, and these virtual connections are then, these constraint conditions can then be created. There is a question. Two questions, three questions, one more question. Vasilis, is it possible to download G models that appear in the webinar to test them locally? For instance, the simple test beam is the preliminary. Yeah. Yes. Okay, we will do that. Yes, we will put this. But be careful. In order to be properly use them, you will need the latest version of ATENA. And some of them, I think, are now part of the ATENA installation. So I think most of the examples that have been presented in the previous webinar and also in this one are part of the new ATENA installation, and they are available in the examples. Okay, Mohammed answered that also. Jan, in the use of 1D beam and 2D shell elements, Francesco is asking for seismic actions. Verification methods have been implemented in pushover or nonlinear analysis type N2 method. I'm not sure now if this is a question or a statement. Yes, well, so if we are using these 1D beam elements and 2D shell elements, of course, they consider the nonlinear effects like the cracking. So they can be used for pushover and nonlinear analysis, also for dynamic. Vinay is asking, is it possible to use 1D beam elements with 6 DOF, 6 degrees of freedom at each of the two nodes for smeared rebars in place of the rebar 1D element with 1 DOF per node? Oh, okay. So whether we can use these new beam elements as reinforcement to be embedded inside the concrete, like we are using the standard truss elements in ATENA. Yes, it is possible, but not very easy at the moment. At the moment, there are actually some examples. If you introduce or if you download the latest ATENA version, 5.7, there is one example how you can do that. Basically, there is a simple trick that you can always use in ATENA. In ATENA, you have this master-slave possibility. So that means you can define this beam element to be inside your solid mesh, and then you can use the master-slave condition to connect them together. So in this way, you can do anything more or less, and you can also use these beam elements inside as reinforcement. But you have to be careful. Normally, ATENA makes an automatic subdivision. So if you define one large truss element inside your model, the program will separate it so that it is nicely compatible with the 3D or 2D solid mesh. But this approach so far doesn't work for these beam elements. So you can embed them inside using the master-slave conditions, but you have to make sure that the meshing or the mesh size is somehow compatible, or at least close enough. There's a question by Sinan. Does the license of new ATENA 5.7 include the using of Git? Well, you not really. Well, I'll put it like this. If you upgrade to ATENA 5.7 and you have an existing license to Git 14, then you don't need to upgrade Git 14 and you can use Git 14 with new ATENA 5.7. But if you want to upgrade also Git to the latest version, which is 15, then you have to also upgrade Git separately. But if you contact our salesperson, they can give you an offer for both upgrades. Nick Hill is asking, how can we predict shear failure for a beam in 3-point bending test using the plastic strain parameter in ATENA? Well, this is a quite, I think, extensive question. I'm not sure exactly where it is aiming. But shear failure in beams, when you model with ATENA solid element, it is typically a tensile failure. So it does not very much depend usually on the plastic strain. So probably it will be best to contact our hotline, which is cervenka.cz, and discuss it directly. What is the particular problem you are experiencing? Francesco, again, in the next version, we will implement constitutive model for soil type, small strain stiffness. Yes, in the coming version, we are planning to have also a constitutive model for soil consolidation, which we expect to be released at the beginning of next year. Edward is asking, are there any Australian engineers connected to the seminar? So please let them know that ATENA is available through our company. Yes, we have a distributor in Australia. So if somebody is interested to have some more questions, they can look at our website or at this chat box and contact this company. Okay, let me continue. We are also running out of time, but so I will just complete with some interesting examples from some practical analysis with ATENA from recent projects. So here is, for instance, an interesting blast analysis of a high-rise building. So ATENA, you may know we have these dynamic capabilities, so it can be used also to simulate blast loading. But I need to make a small note here. In ATENA, we are using implicit solver. So this is done with implicit dynamic analysis. Another interesting feature, which I want to remind you, we have in ATENA is the possibility that once you make an analysis, like in this case of a continuous beam with all the reinforcement, and then you can load it up to failure to obtain some shear failure as it is here. And sometimes it is useful to plot the classical standard engineering quantities like moment diagram or shear force diagram. So you can do that in ATENA Studio post-processor, where you can define various sections. You can have the sections generated automatically. And then in these sections, the program integrates the stresses to obtain the standard shear or shear moment, normal or shear force diagrams. This is the same situation for a little bit more, even more complicated example of a bridge. And here are some high-rise buildings that we also analyzed with ATENA. Actually, even with 3D model, yes, I keep talking about using these new, or having these shell elements and beam elements, but in the end, it was actually quite advantageous, or it was, in the end, we decided it is better to model it by solid elements, of course, with quadratic solid. And then we, of course, for high-rise buildings, it is sometimes very important to check eigenmodes and eigenfrequencies. Then there was some pushover analysis, in this case for wind load. So thank you for your attention. We are out of the proposed time of 1 hour, but of course, if there are some interesting questions or pressing questions somebody may have, we still may have time to answer them. Yeah, let me look at the chat window. Edward is saying thank you. So I also thank you for your attention, and thank you for those of you who are using ATENA. So we are looking forward to hearing from you. And of course, if there are some questions about the new version or about some ATENA features in particular, please use our hotline support. And also we have this forum when some of you are even answering some of the questions without our intervention. So all these possibilities are available now, and I hope you will find ATENA useful for your work, and I'm looking forward to seeing you or hearing you in other webinars that we are planning in the future, and also hopefully soon at some exhibition or conference.
ATENA program produced by Cervenka company. You can find us via the website and download the program from it, or on YouTube by name Cervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.